Exploring Life, Chapter 3, Chemical Bonds Part 2. Most substances around us exist as mixtures, combinations of elements, molecules, or compounds that are not chemically bonded. Since there's no bonding, mixtures can be separated by physical means. Examples include ocean water and air. A solution is a special type of mixture. It's homogeneous, meaning the components are evenly distributed. It consists of a solvent, present in the larger amount, and a solute, in the smaller amount. Solutions can be solids, liquids, or gases. Solution concentration refers to how much solute is present in a given amount of solution. One common way to express this is mass percent, mass of the solute divided by the mass of the solution, multiplied by 100%. In science, we use the metric system. Since water has a density of 1 gram per cubic centimeter, 1 milliliter of water equals about 1 gram. That makes it easy to convert between volume and mass in dilute aqueous solutions. Chemical bonds aren't permanent. They can be broken, formed, or rearranged during a chemical reaction. The substances that enter the reaction are called reactants. The substances formed are called products. This is how matter transforms in chemistry and biology. In chemical reactions, atoms might shuffle partners, but their nuclei stay intact, same number, same type. No identity crisis. That's very different from what happens in stars and supernovae, where we smash nuclei, change elements, and dive into cosmic alchemy. Don't worry, a chemist won't create a black hole. But keep an eye on the physicists. Chemical equations are how we represent reactions. They show what goes in and what comes out. These equations follow the law of conservation of mass. Total mass stays the same before and after a reaction. Atoms aren't created or destroyed, they're just rearranged. That's why the number of atoms for each element must match on both sides. In other words, strive for perfect head counts. We have 3 major types of reactions: synthesis, or combination reactions, form new bonds and require energy, anabolic. For example, A plus B forms AB. Decomposition reactions break bonds and release energy, catabolic. For example, AB breaks into A and B. Exchange reactions involve both breaking and forming bonds. For example, AB plus C becomes AC plus B. All of these are essential to life. Some reactions happen quickly, like when vinegar reacts with baking soda and starts fizzing. Others take much longer. And some reactions can run in both directions at the same time. These are called reversible reactions, where reactants and products continuously shift back and forth until they reach equilibrium. The rate at which a reaction proceeds depends on several factors: the concentration of the reactants, their physical state and surface area, the presence of a catalyst, and the temperature. While all of these are important in living systems, in this module we'll focus specifically on catalysts and temperature. Every chemical reaction needs some energy to get started. That's why things don't fall apart randomly. It takes activation energy. You can think of it as a barrier the reactants need to climb over. A catalyst lowers that barrier. It offers an easier path that requires less energy, so the reaction happens faster. And the catalyst itself? Unchanged and ready for the next round. Catalysts speed up chemical reactions without being used up. They do this by lowering the activation energy, the energy needed to start the reaction. Think of a catalyst like a traffic controller. It doesn't move the cars but keeps everything flowing smoothly. This diagram is a bit complex, so let's break it down. The green blocks on both sides show the molecules before and after the reaction. The vertical axis represents energy. The higher it is, the more energy it represents. The tall purple curve is the activation energy without a catalyst, high and hard to climb. That's why this reaction won't happen easily. The pink curve below it is the activation energy with a catalyst, much lower and more manageable. Blue arrows show how the catalyst lowers the energy required. The product ends with less energy than we started with, meaning this reaction releases energy. The takeaway? A catalyst doesn't change the start or end points, it just makes the path between them faster and easier. Temperature affects how fast reactions happen. Higher temperatures make particles move faster with more kinetic energy. This increases collision frequency and makes reactions more likely. Lower temperatures mean slower particles, fewer collisions, and slower reactions. So, generally speaking, the hotter it gets, the faster things react, up to a point. A good example is how temperature affects metabolic rate. Warm-blooded animals, like humans and birds, maintain a steady internal temperature. That keeps chemical reactions in the body running consistently, regardless of the environment. Cold-blooded animals, like reptiles and amphibians, rely on external temperature. That's why a lizard basks in the sun, to speed up its metabolism. And here's a human example: fever. When you have a fever, it's your immune system's way of speeding things up to fight infection. Higher temperature boosts enzyme activity and immune response. Pathogens don't like the heat. So, while a fever can feel awful, it's your body's way of fighting back. If it's not dangerously high, sometimes it's best to let your body handle it. You've heard many analogies throughout this lecture, some more memorable than others. Now it's your turn. Come up with your own analogies for each of the following concepts: the role of valence electrons, types of chemical bonds, electronegativity, and catalysts. Try to make them creative and relatable. In this chapter, we explored how atoms form bonds, ionic, covalent, and hydrogen, and how those bonds shape the structure and stability of matter. We also looked at solutions, the basics of chemical reactions, and the factors that influence reaction rates. These principles are the foundation for all chemical interactions in biology, from the water in your cells to the energy your body uses every second. In our next chapter, we'll take a closer look at water, its unique properties, its role in life, and why this simple molecule is anything but ordinary. Now it's time to check your understanding of this lecture. These questions are here for self-evaluation. No pressure, just a way to review and reinforce what you've learned.